Hello everyone, in this video we are going to revise a new chapter known as Surface Chemistry. Well, in this chapter we will study about the surface related properties of matters, and the properties are just as adsorption or colloids and emulsions in case of emulsions. Now, there are many phenomena that are dependent on the surface of any material. For example, whenever we use palladium charcoal in case of any reduction process, then the whole reaction depends on the surface of that particular charcoal that we are using. Now, there are many properties of matter which are related to their surface, and such properties become predominant if the substance is in finely divided form or its surface is rough. Therefore, we use palladium charcoal in powdered form so that the surface area increases enormously. We use them as in powder form. So in powder form, surface area increases predominantly. So, the surface related properties of matters are just like adsorption or the colloid states or emulsion. We'll study about them one by one. In case of adsorption, by definition, it can be called as the phenomenon of existence of a substance in different concentrations at the surface of another substance than in the bulk phase. So, this is the phenomenon of existence of a substance in different concentrations. In different concentrations at the surface and at the bulk. At the surface of another substance than in the bulk phase. Now, there are two terms that we frequently use in case of adsorption, and the terms are adsorbent and adsorbates. So, the substance whose surface adsorbs molecular species of another substance is called adsorbent. So, adsorbent is the substance whose molecules adsorbs. And there is another term known as adsorbate, and the adsorbate are the substances which gets adsorbed. So adsorbate, they are the substance which gets adsorbed. Okay, so there are different types of adsorption processes. Suppose if the concentration of a substance at the surface of another substance is more than in the bulk of the adjoining phases is called positive adsorption, or if the concentration of substance is less on the surface than in the bulk, then it is known as negative adsorption. Okay. Now, there are different types of adsorption known as physisorption, types of adsorption. So, mainly there are two types of adsorption known as physisorption. First is physisorption, and the second is chemisorption. So, let's study first about physisorption. So physisorption is nothing but the physical adsorption, and there are many characteristics of physisorption which separate it from chemisorption or chemical adsorption. So it is caused by intermolecular van der Waals forces. So we can say that it is caused by intermolecular van der Waals forces. It depends on nature of gas. It depends on nature of gas, and the heat of adsorption is very small. It's about only 5 kilocalorie per mole. So heat of adsorption is very small. And also, this process is reversible. Please keep in mind that physical absorption is reversible, or physical adsorption is reversible. It forms multimolecular layers on adsorbent surface. It occurs at low temperature. The increase of pressure increases adsorption. So if adsorption increases with pressure, we can say that adsorption increases with pressure. And also equilibrium is attained readily, and it is reversible. Since we have already discussed that adsorption is reversible, therefore there should be an equilibrium. And hence, in this case, since heat of adsorption is also very small, equilibrium is attained. Equilibrium is attained readily. That is, very fast equilibrium will be attained as soon as the physical adsorption starts. Okay. Now it forms multimolecular layers on adsorbent surface. Therefore, if one layer is formed after adsorption, it is possible that other layer may form, and above that one more layer may form. So there are possibility of multimolecular layers. It forms multimolecular layers. And there is another type of adsorption known as chemisorption or chemical adsorption. And their characteristics are, something that is that makes it different from physical absorption, and therefore their characteristics are more or less opposite to that of physical absorption. Now, the first characteristic that we studied about physisorption is that it is caused by intermolecular van der Waals forces, but in chemisorption it is caused by chemical bond formation. It is caused by chemical bond formation. It is much more specific. Although physisorption depends on nature of gas, chemisorption is much more specific and depends upon the nature of both the adsorbent and adsorbent. It depends upon the nature of both, that is the adsorbent and the adsorbent. Okay, and here I should write it, that is adsorbent and adsorbent. Its heat of adsorption is very large. Its heat of adsorption is very large. It is around, its heat of adsorption is around 20 to 100 kilocalorie per mole, whereas in case of physical adsorption, its heat of adsorption is around 5 kilocalorie per mole. Okay. Now, since physisorption is reversible, chemisorption is irreversible. Chemisorption is irreversible and it forms unimolecular layer. It increases with increase of temperature. Since physical adsorption, it occurs at low temperature, but chemisorption increases with temperature. Okay, and in this case, high pressure is favorable. In case of chemisorption, high pressure is favorable. Decrease of pressure does not cause desorption. So here high pressure is favorable. High pressure is favorable. And equilibrium is attained very slowly. Whereas in case of physisorption, equilibrium is attained very readily. In this case, equilibrium is attained slowly. And the last point that we discussed in physisorption is that it forms multimolecular layer, but in case of chemisorption, it forms unimolecular layer. It is because once the unimolecular layer or once one molecular layer is formed, that reaction site has been occupied, and therefore there is no possibility for another reaction at that place, and hence it forms a unimolecular layer because that reaction site has been occupied. Now let's discuss about adsorption of gases in solids. Adsorption of gases in solids. Well, in this case, the extent of adsorption of a gas on the surface of a solid depends on number of factors, and the factors are depends on the following factors. First one is nature of gas. Well, since physical adsorption is non-specific in nature, any gas will be adsorbed on the surface of a solid to some extent or other. However, under any given conditions of temperature and pressure, easily liquefiable gases such as NH3 or NH4 or HCl or Cl2, they are adsorbed more than permanent gases like H2, O2 or N2, etc. Whereas in case of chemisorption is specific in nature, therefore only those gases will be adsorbed which form chemical bonds with it. So in case of nature of gas, in case of physisorption, any gas will be adsorbed to some extent or the other, but chemisorption is specific in nature. Only those gases will be adsorbed which form chemical bonds with it. Well, the other factor is nature of solid. Now, activated charcoal is most common adsorbent for easily liquefiable gases that we have already discussed just now. So, poisonous gases such as H2S or COCl2, they fall in these group for easily liquefiable gases. Therefore, it is used in gas mask. Other gases such as oxygen, nitrogen or hydrogen, they adsorb more on metals such as nickel, platinum or palladium at high temperature. So therefore, depends on the extent of adsorption, and adsorption depends on the nature of solid that we are taking under consideration. Now, specific area of solid, yes. Since I have more area to occupy, I will choose that spot which is providing me that much of area where I can rest. Okay, so this is the case for adsorption also. More area available to the adsorbent, Okay, more area available to the adsorbent, more readily adsorption will be taken place. Therefore, it depends on specific area of solid. Okay, pressure of gas. Since we have already discussed here that in case of physisorption, adsorption increases with pressure. Okay, this point. And in case of chemisorption, high pressure is favorable. Therefore, on pressure of gas, it is dependent. Adsorption depends on pressure of gas. Pressure of gas. And if we plot something, if we plot x by m is the extent of adsorption, where so extent of adsorption is x by m. Extent of adsorption equals x by m, where m is the mass of adsorbent and x is that of adsorbate, where x is the mass of adsorbate and m is the mass of adsorbent. So the extent of adsorption, it depends on pressure, and if we draw a graph between extent of adsorption and pressure, then we get a graph like this. This is x by m, this is pressure. So initially the graph will increase linearly and then suddenly it will attain a saturated value. So the pressure at which the gas at which the adsorption attains the saturated value, it is known as PS, that is saturated pressure. Okay, so after this point, after PS, beyond this point, the adsorption remains constant. So since here we can see that at low pressure x by m varies linearly with gas. You see this area, this region, it throughout this region, it varies linearly with x by m varies linearly with pressure of gas. So therefore, at low pressure, x by m is directly proportional to P raised to the power 1, or pressure of the gas. So from here, x by m equals Kp at low pressure. But at high pressures, since now adsorption has become independent of the pressure of gas, since it has already achieved a saturated value. So therefore, at high pressure, adsorption, that is x by m, directly proportional to P raised to the power 0, that is, it is independent of pressure. Therefore, we can say that extent of adsorption equals a constant quantity. Now, at intermediate pressures, now this region now we are talking about, at intermediate region. So, at intermediate pressure, the variation of x by m versus P can be expressed as x by m at intermediate pressure. Okay, so at intermediate pressure, x by m equals K P raised to the power 1 upon n. And this equation is known as Freundlich, Freundlich adsorption isotherm. Remember this concept. One question has been asked based on this concept only, although it was a theoretical question. So where here n is greater than 1, and if we simplify this expression further, we get something like log x upon n, log x upon n equals log k plus 1 upon n log p. Okay, and hence if we draw a graph between log x by m, so if we draw a graph between log x upon m and log p here, we get a straight line. whose slope is given by 1 upon n, or we can determine the value of n from the slope between log x by m and log p, and the intercept gives us the value of log k, that is the value of constant. So from this graph we can identify the value of we can identify the expression for Freundlich adsorption isotherm. Now in case of temperature, there is another parameter on which adsorption depends. Here after pressure we have discussed here 4 parameters, so there is fifth one, and the fifth one is temperature. So in case of temperature, now physisorption depends in different manner than chemisorption. Let's discuss two different graphs for physisorption and chemisorption. Here is the extent of adsorption, that is x by m. Here is temperature, T. Here the same parameters are there, x by m and T. Okay, so in case of physisorption, adsorption depends on this manner, just like this is known as adsorption isobar. If the temperature is constant, pressure is constant. So the adsorption is accompanied by release of heat energy. So in accordance with Le-Chatelier's principle, the increase of temperature should decrease the extent of adsorption. And this has indeed been found to be so when experimented. So a plot of x by m versus temperature at constant pressure is known as adsorption isobar. So this is the case for physisorption. This is for physisorption. And this is for chemisorption. In case of chemisorption, the isobar has been identified somewhat like this. It increases first almost linearly, and then it goes to maximum, and then it decreases. So the initial increase is due to the fact that chemisorption requires activation energy. Okay. So in case of physical adsorption, x by m decreases with increase in temperature, whereas in case of chemisorption, x by m initially increases with temperature and then decreases as shown below here. But it is first increasing here, and then it is reaching maximum at this point, and then it is decreasing. So the initial increase is due to the fact that chemisorption requires some amount of activation energy, because here chemical bonds are getting formed. Okay, so the one more parameter on which adsorption depends is the activation of solid. Well, activation of solid or adsorbent, it means increasing its adsorbing power, nothing else. So here activation of solids, there is one more factor on which adsorption depends, and it just means increasing its adsorbing power. Increasing adsorbing power of adsorbent. That is why we have used a term called like activated charcoal. That is the activated solid. So this is increased by increasing the specific area, either by making the surface rough or by breaking the solids into smaller parts. So if we make a solid in powder form, then we are increasing the surface area of solid manifolds. So that is why, since total amount of area to get adsorbed increases, so this property is known as activation, because by making the solid into different parts in its powdering form, we are increasing the surface area, and hence we are increasing the adsorbing power of that particular adsorbent. Okay. So let's discuss about adsorption from solution. Now some solids are capable of absorbing certain solutes from the solution. So and this property is made use of in adsorbing coloring matter from solutions of organic substances. So adsorption from solution. So in this case, In this case, the amount of or the extent of adsorption, that is X upon M, it equals Kc, just like the pressure. It depends on Kc to the power 1 upon M. So fluid adsorption isotherm is also applicable to solutions. Now, if we replace the pressure term by concentration of adsorbate in solutions. Okay, so this is the concentration of adsorbate in solution. So this is the case. Now, applications of adsorption, there are many applications. So applications of adsorption, they are used in many areas. For example, in case of chemistry, it is used in gas mask to remove poisonous gases. So first, maybe to remove poisonous gases. It is as an ion exchange resin to remove hardness of water. So it can be used to remove hardness of water. And it is used in chromatographic adsorption. Okay, and now there are many more that are there are many more properties of adsorption which finds application in various areas. For example, to control humidity, silica gel is used because of its hygroscopic property and the catalytic effect of number of catalysts. So it is used as catalyst, and it is to remove humidity. So these are only some of the applications of adsorption that you find in daily use, or in almost in daily use. So let's study something about catalyst. Now remember that catalyst does not alter the end point of the reaction, and it remains unchanged in amount and chemical composition at the end of the reaction. Yes, it may get changed, it may get a considerable change, it may undergo a considerable change in physical form, but as far as amount and chemical composition is considered, at the end of the reaction they remain unchanged, and the small amount of catalyst is capable of producing the desired effect. We do not need very much amount of catalyst in order to achieve our goal. So catalysis, let's study about catalysis. So in case of catalyst, it does not initiate a reaction, it merely accelerates the reaction that is already occurring. So catalyst is working in the following form. Suppose this is the energy of any reaction, this is the reaction coordinate. Well, the concept of reaction coordinate is very much complex. You will be studying about it if you choose chemistry later. That reaction coordinate comes in when you go to the quantum level of any reaction, then you will find the real application of reaction coordinate. Well, in case of reaction coordinate, there is a particular amount of energy for reactants, and then the reaction of, or the energy of reaction increases, and then it undergoes the formation of products. And this energy is known as activation energy. Suppose this is the cases. So this energy is known as activation energy of any reaction. So the work of catalyst is to reduce the activation energy so that the reaction can be accelerated. Hence, in case of catalyst, the graph that we obtain is somewhat like this. Now see, the end point and initial point are unaltered. Okay, so in case of catalyst, it reduces the activation energy of any reaction. So this is the case in presence of catalyst. So a catalyst increases the rate of reaction by producing a pathway whose activation energy is lower than the activation energy of uncatalyzed reactions. So there are many types of catalysis known as positive catalysis, in which a catalyst increases the rate of reaction, negative catalysis, or we also known as inhibitor, or in case of negative catalysis, activation energy gets increased. So it reduces the rate of reaction. Or autocatalysis, in which products itself act as a catalyst, or homogeneous catalyst, in which a reaction and catalyst they are in same form. In case of heterogeneous catalyst, reaction and catalyst, reactants and catalysts are in different forms. Okay, so there are different types of theories of how a catalyst works. So there is an intermediate compound formation theory. Remember that there is not a universally accepted theory for catalyst working. So let's discuss something about intermediate compound formation theory. Compound formation theory. So in this case, suppose there is a reactant A and there is a catalyst C. They undergo a reaction, they form AC, and then AC, it reacts with B and it forms AB, and it gives off catalyst C again. So this is the reaction that takes place in the presence of catalyst, and the net reaction is A plus B giving us AB. So in the presence of catalyst, an intermediate is formed known as AC, and then AC undergoes reaction with B which forms AB, and the rate is equals K into A into C, because this is the rate determining step, RTS. Okay, so this is intermediate compound formation theory, and there is adsorption theory, in which a catalyst undergoes in which the products or the reactants undergoes adsorption on catalyst surface, and then they form product by diffusion. So the process that is followed, the pathway that is followed in case of adsorption, is the diffusion of reactants on the surface. First the reactants get diffused, and then some form of association between catalyst surface and reactant occurs, occurrence of chemical reaction on catalyst surface, and desorption of reaction products away from catalyst surface, and then diffusion of reaction products away from catalyst surface. So these occur in case of adsorption theory. Adsorption theory. The processes that are occurring is, first is diffusion of reactants, and then some association between catalyst surface and reactant, association between catalyst surface and reactants, and then occurrence of chemical reaction, then it forms desorption. The opposite of adsorption is desorption of products away from catalyst surface, and finally diffusion of reaction products away from catalyst surface. This is how the adsorption theory works in case of catalysis, diffusion of products away from catalyst surface. So okay, now let's discuss about the colloid state, another concept in this chapter, colloid state. Now we know if we mix salt into water, then a true solution or a clear solution is obtained. That is known as a true solution. But if we put a little bit of soil in water, then we do not get a clear solution. The solution that we get through this type of mixing is colloidal solution. So the nature of substance, whether they are crystalloid or colloid. It depends upon the size of solute particles. Okay, so the true solution that we are getting is the crystalloid, and the solution we are getting due to mixing of soil and water is called colloid. So the nature of substance, whether crystalloid or colloid, it depends upon the size of solute particles. When the size of solute particles lies between 1 nanometer to 100 nanometer, it behaves like a colloid. Remember that size of solute particles, it lies between 1 nanometer to 100 nanometer in this case. If the size of solute particles is greater than 100 nanometer, it exists as suspension, and if particle size is less than 1 nanometer, it exists as a true solution. Just like adsorption, we get here dispersion phase and dispersion medium. So the component present in small proportion and consisting of particles of colloid dimension is called dispersed phase. So, and the medium in which colloid particles are dispersed is called dispersion medium. So colloid particles here, colloid particles are called as dispersed phase, and the medium in which colloid particles are dispersed is called dispersion medium, and the medium is called dispersion medium. Okay. Now there are 8 types of total colloid solution, and when a solid acts as a dispersion medium and the dispersed phase is solid, then the colloid solution is known as solid sol. Or if dispersed phase is solid, dispersion medium is liquid, then it is known as sol. Or if dispersed phase is solid and the dispersion medium is gas, then it is known as aerosol. So in total there are 8 types of colloidal solutions. So they form 8 types of solutions. 8 types of colloidal solution. Okay, so now if colloidal solution has fluid-like appearance is called sol. Remember that if colloidal solution it has fluid-like appearance, it is called sol. Okay. Now there are classification on the basis of interaction between different phases. So there are different types of colloids known as lyophilic colloids. You can remember this term by using this lyophilic. Philic means solution loving. Okay. So lyophilic colloids, they are the colloids in which the colloid particles or the dispersed phase and dispersed medium, they like to be with each other, and such colloids are reversible. So we can say that they are solution loving colloids. And they are reversible. Remember, they are reversible. Therefore, in case of lyophilic colloids, the solids are obtained after evaporation of medium, and they can be easily brought back to the colloidal state by shaking the solids with the dispersion medium. Okay, so just by shaking we are achieving our goal. So therefore, this is known as this is a reversible colloid, and we have many examples such as starch or proteins and certain polymers. They are lyophilic colloids. And if water is used as dispersion medium, the colloid is known as hydrophilic colloids. And there is another type known as lyophobic. Lyophobic colloids. Now, in case of lyophobic colloids, they are just opposite to the lyophilic colloids. They are solution fearing or solution hating. They are solution fearing colloids. And they are irreversible. That is, if we have separated the dispersed phase from dispersed medium, it is not easy to get the colloid back just by ordinary processes like shaking or anything. Okay, so special methods are used to get back them. Okay, so these are irreversible colloids. Okay, now the differences between lyophilic and lyophobic colloids are many. For example, in case of lyophobic source or lyophobic colloids or lyophobic source, colloid particles are electrically charged. Their stability is due to electrical charge. Viscosity is similar to that of dispersion medium. So there are some differences between them based on these properties of solution fearing or whether they are solution loving. Remember that Tyndall effect is exhibited by lyophobic colloids. Remember this term. The Tyndall effect is exhibited by lyophobic colloids or lyophobic salts. Okay. Now let's discuss that there are classification based on the nature of colloidal particles, and the classifications are multimolecular colloids, macromolecular colloids, or associated colloids. So there are multimolecular colloids, or macromolecular colloids, and associated colloids. In case of multimolecular colloids, when on dissolution a large number of atoms or smaller molecules of a substance aggregate together to form species having size in the colloidal range. Okay, so just as the name suggests, when different atoms or large number of atoms or molecules they come together, they aggregate together to form species that have a size in colloidal range. And in case of macromolecular colloids, colloidal particles are themselves large molecules having colloidal dimensions. Okay, so one molecule, they are formed by aggregate of small molecules. In this case, one molecule is big enough. One molecule is big enough. And in case of associated colloids, these include substances which behave as true solutions at low concentration but became colloidal in nature at high concentrations. At high concentrations, they become colloidal. Okay. Now, there are many methods to prepare colloidal solutions, just like lyophobic salts can be prepared by condensation methods or dispersion methods, and in case of by physical methods, they can be prepared by exchange of solvent or excessive cooling. So some of the methods are there. So now we'll discuss about Michaelis. That we know that in case of soaps, there is a hydrophobic tail. This tail is hydrophobic, that is, it hates water, whereas it has one head which is hydrophilic in nature. Okay, so it has one head which is hydrophilic in nature, and there is a tail which is hydrophobic in nature, Now, whenever these molecules, or whenever soap is immersed in water, hydrophobic gel, they aggregate themselves away from water. They tend to be away from water. Therefore, they aggregate here like this. And the head, they tend to be here. Okay, so they form this type of structure, a circular type of structure, which are known as micelle. This structure is known as micelle. So, for example, C17H33COO negative. So this is tail, this is head, and these species, this is hydrophobic and this is hydrophilic, and these species, when immersed in water, they form this type of structure, and therefore whenever they get out of water, they tend to be out of water. Whenever they get out of water, they take certain kinds of stain with themselves, and that is why these get cleaned. The clothes or whatever we are intend to clean, these gets cleaned because these micelles get out of water, taking away with them some stains or oil properties or anything. Okay, so let's discuss about coagulation or flocculation of colloid solutions. Now, the precipitation of colloidal solution through induced aggregation by the addition of a suitable electrolyte is known as coagulation. And the minimum amount of electrolyte in millimoles that must be added to 1 liter of colloidal solution so as to cause its complete coagulation is called flocculation value of electrolyte. So, the minimum amount of electrolyte in 1 liter that must be added to cause complete coagulation is called flocculation value of the electrolyte. Okay, and the coagulation value of electrolyte, it varies from electrolyte to electrolyte. So the Hardy and Schulze studied the coagulation behavior of various electrolytes and presented their observations in the form of Hardy-Schulze rules, which states that the ions carrying charge opposite to that of Sold particles are effective in causing coagulation of the Sold. Coagulation power of electrolyte is directly proportional to valency of ions causing coagulation. So there are some of the rules meant for this to find the flocculation value, but remember that some data are given in the question, and based on this you find the total number of millimoles that is required to cause the complete coagulation of a colloidal solution, and that is known as the flocculation value. Now, the protecting power of a protective colloid is expressed in terms of gold number. Remember that the number of milligrams of the protective colloid that just prevents coagulation of 10 ml of standard gold soles. So the number of milligram of the protective colloid that just prevents coagulation of 10 ml of standard gold soap when 1 ml of 10 solution of NaCl is added. So this is known as the gold number of a colloid. So remember this definition, that the number of milligram of the protective colloid that just prevents coagulation of 10 ml of standard gold solution when 1 ml of 10% solution of NaCl is added. So this is known as the gold number of colloid, and the smaller the gold number of protective colloid, greater will be its protecting power. We will discuss some questions on gold number just now. So have this definition in mind, and now let's discuss some of the questions. So before discussing questions, I must tell you that the majority of questions in IIT JEE are theoretical from this chapter. So therefore, we have discussed theory extensively so that you can have a firm grasp on theory of this chapter. So go through the theory very well, because majority of questions are asked from theory only from this chapter. So very small amount of numerical questions are asked. I don't know last time when numerical question was asked from this chapter. So very small amount of numerical questions are asked. So let's discuss a few questions. Very small amount of questions we'll be discussing based on numerical type. So first question, it is saying that the coagulation of 100 centimeter cube of gold solution is completely prevented by addition of 0.25 gram of starch to it before adding 10 ml of 10% NaCl solution. The gold number is. Okay, so the gold number of starch is the milligrams of starch added to 10 ml of standard gold solution just to prevent coagulation of gold salt when 1 ml of 10% NaCl is added to it, or 10 ml of 10% NaCl is added to 100 ml of gold salt. In other words, 1 ml of 10% NaCl is added to 10 ml of gold salt. Okay. So in this case, in this case, 10 ml of 10% NaCl is added to 100 ml gold salt. Okay, so we can also write it as 1 ml of 10% NaCl is added to 10 ml gold salt. Okay, now quantity of starch added to 10 ml of gold salt is, okay, since in 100 ml of gold salt 0.25, since in 100 ml gold salt 0.25 gram of starch was added. This is also equal to, or 250 milligram was added. Okay, so therefore in 10 ml gold salt, we can say that 25 milligram of starch was added. Okay, so in 10 ml gold salt, since 25 ml of starch is added, and we know that gold number of starch is milligrams of starch added to 10 ml of standard gold salt, just to prevent coagulation of gold salt when 1 ml of 10% NaCl is added to it. So therefore, according to given conditions, 25 milligram of starch solution satisfies this condition, and hence gold number equals 25. This is the answer to this question. Okay, so let's come to another question. And the question says, a sample of charcoal weighing 6 grams was brought into contact with a gas contained in a vessel of 1 liter capacity at 27 degrees Celsius. The pressure of the gas was found to fall from 700 to 400 millimeter of Hg. Calculate the volume of the gas that is adsorbed per gram of adsorbent under the condition of the experiment. The density of charcoal sample is 1.5 gram per centimeter cube. Now, the adsorption is taking place in a closed vessel here. Thus, when pressure falls, there is correspondingly increase in volume, and to keep volume constant, excess of volume of gas would be adsorbed. Remember, I repeat it again, the adsorption is taking place in a closed vessel here. Therefore, since adsorption is taking place in closed vessel. Okay. Therefore, when pressure falls, there is correspondingly increase in volume. And now, since the vessel is closed, therefore, to keep the volume constant, excess of volume of gas would be adsorbed. To keep volume constant, excess of volume of gas would be adsorbed. Okay. Now, using P1 V1 equals P2 V2, we know this is valid for an ideal gas, and since here we are considering them to be ideal, therefore P1 V1 equals P2 V2 at constant temperature. So from here we get V2 equals P1 V1 upon P2. So V2 comes out to be 700 into 1000 upon 400. Since the pressure has fallen from 700 millimeter Hg to 400 millimeter Hg, so from here V2 is 1750 milliliter. Now, actual volume of flask is 1000 minus volume of charcoal. We know this, that actual volume of flask equals 1000 minus volume of charcoal. Okay, so the volume of charcoal here, 1000 minus volume of charcoal here is 6 upon 1.5, because weight is here 6 and the density is 1.5 gram per centimeter cube. Weight is 6 gram, therefore volume comes out to be 6 upon 1.5. So from here we get the actual volume of flask as 996 milliliter. Now the volume of gas adsorbed, equals 1750 minus 996 equals 754 milliliter. Okay. So the actual volume of flask is 996 milliliter. The total volume is 1750 milliliter. Therefore, volume of gas adsorbed is 1750 minus 996 equals 754 milliliters. Now, therefore, the volume of gas adsorbed per gram of charcoal. Therefore, volume of gas adsorbed per gram of charcoal equals volume 754 milliliter upon mass equals 125.67 milliliter per gram. Now, volume of gas adsorbed per gram at STP thus comes out to be using the ideal gas equation. Since total number of moles is constant, okay, therefore volume of gas adsorbed per gram at STP, since we know that P1 V1 upon T1 equals P2 V2 upon T2. Okay. So if we use this, we get the volume equals, we have used this equation, so volume comes out to be 125.67 milliliter per gram into 400, that is pressure, into 273 STP temperature, upon 300 into 760. Okay, so 300 is the T1, that here 300, that's 27 degrees Celsius. So initially it was contained in 27 degrees Celsius. To calculate the corresponding values at STP, we have used this identity, and then from here we get the value of volume as, so volume comes out to be 60.19 milliliter per gram. This is the answer. Okay, so let's move to another question. And the question is asking us, or it is saying that a solution of palmitic acid in benzene contains 4.24 grams of acid per decimeter cube or per liter. When this solution is dropped on a water surface, the benzene evaporates and the palmitic acid forms a monomolecular film of the solid type. If we wish to cover an area of 500 centimeters square with a monolayer, what volume of solution should be used? The area covered by one palmitic acid molecule may be taken to be 0.21 nanometer square. Okay, so to solve this problem, let the volume of palmitic acid solution required to cover the desired area of 500 centimeters squared be VML. Let the required volume is VML. Okay, so therefore number of molecules of palmitic acid in VML is, therefore number of molecules of palmitic acid in VML, it equals 4.24 into V into 6.023 into 10 raised to the power 23 upon 1000 into molecular weight, that is 256. Okay, so from here the volume comes out to be, its benzene contains 4.24 gram of acid per decimeter cube, therefore this is the total number of moles, this is volume, and this is the Avogadro number here. So from here the total number of molecules, which comes out to be 9.976 into 10 raised to the power 18 into V. So therefore the area covered by these molecules, so the total number of molecules is this, and now here area covered by one molecule is 0.21 nanometer square. Therefore area covered by these molecules, it equals to 9.976 into 10 raised to the power 18 into V, or to write somewhere else so that we can have space. So area covered by this molecule, it equals 9.976 into 10 raised to the power 18 into V into area covered by one molecule, that is 0.21 into 10 raised to the power minus 14 centimeters squared. So we have converted 0.21 nanometer square into centimeter square. So this comes out to be this value. And now, but this area is equal to 500 centimeter square. This is given in the question. This area should be equal to 500 centimeter square. So equating this to 500, if 9.976 into 10 raised to the power 18 into V into 0.21 into 10 raised to the power 4 minus 14 equals centimeter squared equals 500 centimeter squared. So from here we get the value of V as 0.024 milliliter. So the required volume is 0.024 milliliter. Okay, so let's discuss one more question. The question says that methylene blue from its aqueous solution is adsorbed on activated charcoal at 25 degrees Celsius. For this process, the correct statement is: the adsorption requires activation at 25 degrees Celsius. The adsorption is accompanied by decrease in enthalpy. The adsorption increases with increase of temperature. The adsorption is irreversible. See, this is a totally theoretical question. So from the concept of physisorption and chemisorption, we know that adsorption of methylene blue on activated charcoal is physical adsorption. This is physical adsorption. Okay, and hence first one is incorrect. The last one, the adsorption is irreversible. This is the characteristic of chemisorption. Therefore, this is also incorrect in this case. The adsorption increases with increase of temperature. This is also incorrect. So the correct statement is the adsorption is accompanied by decrease in enthalpy. And this is indeed the case in case of physical adsorption. So in case of physical adsorption, it is characterized by decrease in enthalpy. And since adsorption of methylene blue on activated charcoal is physical adsorption, therefore option B is correct. And this question has been asked recently in IIT JEE 2013 or JEE Advanced 2013. Okay. So go through the theory of this chapter to the best of your ability, because this can be really scoring. You can score 6 to 7 marks very easily by just reading the theory. So that's all for this chapter. Thanks for watching.